So we talked about transformation matrices as mapping, right? From one frame to another, when you wrote the transformation matrix or rotation matrix, you looked at it, this is mapping from one frame to another. Jacobian is the same thing, it's a mapping. But what it does is it maps the inputs to output, meaning that how changes in input will impact the output. Now, if your system has different inputs, 3, 4 inputs, they can impact the output of your system differently, right? Jacobian will tell you like, okay, let's just write this model, create this model, and then we don't care how the input changes. We always feed it in this to this mapping, and it would tell us where the output is. Why it is good? Why it is useful for us? So if you think about the articulated manipulator, which is a robotic arm, leg, any of those, right? Industrial robots. What are your inputs? What are the things that change? So forward kinematic, think of forward kinematic, all right? And it was one of the questions in the concept. But what does forward kinematic do? The change of angles, right, in your joint angles, you're manipulating the position orientation of the end effector. That's what forward kinematic tells you, right? So the variable for your robot are the joint variables. The output is the position and orientation of your end effector. So if we could relate these two together, then doesn't matter how they're changing, we always know what the output is. Now, you would say that okay, for position and orientation, we already know forward kinematic. But then we want to know the velocity because a lot of times we control the velocity, right? Especially in industrial robotics, how fast you move, where do you stop, right? And that's not about position, that's about the velocity. So to do that, we need to have velocity kinematic expression. To write that, we need that mapping. Jacobian is that mapping, right? So we're going to start from mathematical definition, how it is done directly. We can apply this to our examples. So this is a direct method. Then on Friday, we will learn that there's an easier way to do this. Okay, that's for Friday. And then we will usually use that because it's a lot easier when you don't actually know how your robot works, right? So the direct method tells you that if you have a function f, has some input and some output. So in here, this is your output, these are your input, right? So input q to f, it does something to it and gives you x. You can extend it as vectors, so you're talking vectors. So output or the state of the system, position velocity, is a function of some inputs. Now, we can say that we can write a partial differential, we can get the partial differential derivative of every of these functions, sub-functions, let's say, with respect to the value. Meaning that, okay, this is my arm, right? How does the position of my wrist change if I made a slight change in my shoulder? Now, how will it change if I make a slight change in my elbow? This is going to put them all together, so you have a matrix that has seen all the possible changes to your system because of your input. The easiest way to remember this, you don't have to memorize it, is that if this is your output, and these are your functions, sub-functions, the columns are the variables. Now, depending on how many sub-functions your system has, you're gonna write, so you're getting, so I think I'll do it backwards to make it more like a matrix. So I'm gonna highlight the function. So here is your F1. So we are getting the partial differential of F1 subfunction 1 with respect to all the variables. Then subfunction 2 with respect to all the variables, right? Until we exhaust all of our subfunctions. So these also, these variable always remain the same. So this is variable Q1, for example. So F1, F2, F3 to Fm, all partial differential with respect to your first variable, second, third, fourth. Right? So rows and columns are depend on subfunction and number of variables that you have. So this is your direct method. How are we going to use? Let's use a mathematical example of this before we go to the robotic part. So consider function f from the subset of 2 to R2 to R2. So we have two input to output. And our we have x and y that are the output of F1, F2. Now, what is F1 and F2? F1 and F2 are two expressions that they are function of x and y. All right. We want to write the Jacobian for this. We use the direct method for getting the differentiation or derivative of them with respect to their variables. So I'm going to write, just make it easier, F1 is x squared y, F2 is 5x plus sine of y. You see that you have two variables there. So I'm going to create partial of F1 with respect to x, my first variable, right? Which is hopefully that you know that. If not, you gotta review a little bit of partial differential. And then I'm gonna write partial of F1 with respect to the second variable. So still working on this guy. So getting the partial with respect to all the variables. Now here it becomes x2 because y is the variable and x2 count like acts as a fixed value. Then now there's no more variable in F1. I'm going to move on to F2. Sorry if this is boring and repeated, but I got to do it. So F2, 5x plus sine of y with respect to x is only 5 because sine of y will become 0. And then F2 with respect to y this time. So this doesn't have y in it. This will be cosine of y. Now, I can now say that Jacobian of f of x and y is F1 x, F2 with respect to x, x stays the same, then F1 y with respect to y, then F2 with respect to y. Again, y stays the same. 2xy, x2, 5 cosine of y. Now, why is this useful? Because I can say, so this is the Jacobian of my system, right? So if I say, what would the output of system would look like if my inputs were, for example, at x and y were y and 1 and 0. So we know, so what would the Jacobian look like for a very specific case of x and y be 1 and 0 as input? Then the Jacobian would be 0, 1, 5, 1. You just replace those numbers. So you only have to do this one time. Then we can use this Jacobian and relate it to the, okay, this is how the system will deform, how the system will change. Now you can multiply it by the input vector and cut off, you'll get it. Now, if you think about forward kinematic, what is your input vector? Thetas, your variables, right? Yeah, I remember that we called Q at some point, like all the joint variables, because it could be revolute or prismatic. So when you say theta, still correct, but you need to think that this could be also prismatic. So if your inputs are your joint variables, you have your Jacobian, then you would know what your output would look like at all times. Now, to form the Jacobian, in this example, I gave you F1 and F2, right? For a specific robotic system, for a manipulator, how do we find F1 and F2? Or our functions? How do we know first how many we have? And then how do we find it? That's the big question. Because the inputs are, look at all the joints, there are your input variables. Outputs are position and velocity. Like the meat is, the question is like the model, right? So you always end up with what's the model of this system? Makes sense a little bit, maybe? Okay. All right. Before we go to the example of the robots, I'm going to show you why you could use Jacobian here. All right. So this is just sit back, relax, just listen. So this is my end effector. So I know this end effector would have some position and orientation. Let's say X, Y, Z, theta X, theta Y, theta Z. So this is position, orientation. This was your exam question again. Now, in forward kinematic, we said if we know where thetas are, we can derive an expression that will give us this X vector, right? We know the position and orientation of the end effector. Now, if we think about instantaneous kinematic, what does it mean? If we move everything a little bit, if we move all the joints delta theta by a little bit, is it still like kinematic? Like, is it still not big motion, right? It's partial. So we can look at instantaneous, still kinematic. We haven't gone to dynamic. We froze time, move, and we're looking at it again. So we can say that delta theta could also tell us the little change in position and orientation. That's what forward kinematic does. Now, if we add these two up, theta plus delta theta to X plus delta X. So partial motion of every joint should result in partial motion of your end effector. Now, if we keep doing this, the rate of this change is the velocity, right? Over time. So keep changing this over time, that's our velocity. Agreed? So I can write this, if I do this over time, this is theta dot that give me X dot. So the velocity of the joints, I should be able to find an expression that gives me the velocity of end effector. Now, what kind of velocity your end effector could have? So linear velocity, angular velocity, remember? So like it comes from, so you've seen the vectors in the forward kinematic, right? So it is along those axes. So we know what kind of velocity we get. And here we have these axes. So if I know the velocity of these, I should know the velocity of that. So let's pause here for a few seconds and come out of equation and mathematics and go to actual. What are the joints made of? What is? So if you were to build a robot and your robot has a joint, what you do? What you buy? Represent this one to be the joint. Motor, right? Because actuator has to move on their own, right? Power. For prismatic, it is just linear actuator. Okay. Can you control the speed of your actuator? Does your actuator have a speed? It do. That's theta dot. That's the speed of your joint. Now, by controlling the speed of those joints, all of them, you're actually controlling the speed of your end effector. So think about it, you're working in NASA and you're installing an antenna or something, and then at the end you have to be very careful with precise velocity control because you want to place and you don't want to crash into another structure. The speed control becomes very important. So we need to find an expression that we can relate these two together. That is our velocity kinematics. And we said that if I knew how the joints are mapped and how the input impacts output, I could control the velocity. So Jacobian would be playing that part. So for velocity kinematic, that's it. That's the expression. Compared to forward kinematic for position and orientation, how different they are. There's a lot of upfront work to find that expression. So you don't have much work. It's just calculating the Jacobian. Now, how do we find Jacobian? That is the work. So once you have the Jacobian, everything is done. You're already done. So if you wanted to expand this and write what does it look like that we just talked about, x dot is that x dot, y dot, z dot, and then theta x dot, theta y dot, theta z dot. Linear velocity and angular velocity of your joint, right? Of the end effector.
Why is it theta dot equals building x dot, not x dot?
I'm thinking it's related to the mathematics. Good question. It should be, right? Should be. Okay. In fact, it should be. Because why? Which was the output which should be? So your output, sorry, is equal to Jacobian times your input. So this is mapping. This is the relationship, right? So this shows mapping is not the expression that's put. So this is the end effector's velocity. This is what you're trying to find out. These are the inputs, geometry. All right. So officially, given a representation of end effector, which you need to find out where it is, that function there. Once you have it, you can use direct derivative to find out your Jacobian, and we call it fragment. Now, the Jacobian will have two portions. One will be related to the linear velocity, one related to angular velocity. All right? We will find out a few interesting things about Jacobian once we start solving a few problems. We're going to start with a very simple problem. A 2R articulated R, right? So if I ask you what does the velocity kinematic look like, the expression, you would say, well, I have theta 1 and theta 2, right? Those are my joint variable. And I know my end effector is going to be, well, x1, x2, and two angular velocities, right? So you already know how does it look like. So where's the question? This x dot is j theta. You already know what x dot is. You already know what theta dot looks like as an expression. So what is it that you're looking for? What is it you're trying to solve? Huh? J. So how do you find the Jacobian? What do you need? Functions, right? So what does it mean to find the function? What is it that you're trying to find? So we were interested in end effector, right? Because we're trying to find the velocity of the end effector. So if you can find expressions that tell us where the end effector is, then we can get the partial derivative with respect to all our inputs and then form the Jacobian. So that's always the hard part, to understand what is it that I'm looking for. All right. Now, for the direct method, because I want to have two functions that shows where the end effector is. Okay. You can go by a very simple method. So first of all, this is your z-axis, right? So this could be your x and then your y. And this is your end effector. I know that I need to create f theta 1 and theta 2. How would you go about this? What would be the function that you would write that will represent your end effector? It was a question, it wasn't a mistake. I'm looking for an answer. So I was trying to find a position, right? So with the x, with the y, I have two functions. I can get the, because there's theta in it. So I'm gonna get partial differential and find. It is mapping the position of the end effector. Great. I'm gonna do that. Because this is a 2D robot, it's simple robot, we can do that. So anytime you have 2D robot and you want to write the position of your end effector, because you know the orientation, right? It's in 2D, so it's not gonna change much. You just have Z as your location. So write X of end effector and Y of end effector with respect to your fixed pair. So you're trying to find X of end effector and Y of end effector. So this is your end effector. And we always do that in our fixed pair. Someone check that I have my sine cosine correctly. Should be, but you know me. Thank you. There you go. See? Always worth checking my work. This is your Jacobian, right? I found F1, F2. Now you have to get the partial differential for this. All right? So hold your thought. I want you to kind of stop here because I want to tell you what's your class participation. So you will be working on your class participation. But before that, so did everybody understand what happened here? We needed functions that would explain what is happening to our end effector, right? Represent our end effector. We thought is 2D. Let's write xy position. They have theta 1, theta 2 in it, so roll the expression, and we know we can use direct method for Jacobian. Now, I'm going to show you class participation, and then you're going to write toward that. So your class participation would be for that same 2R. Once you found the Jacobian, I've given you values to find the numerical value for that matrix. All right. So just like what we did for the mathematical expression. So find the Jacobian, then plug in these values, and then you have the matrix. Don't submit it because then I want to talk about singularities, but have it up to there. So I'm going to give you a little bit of time to work this one on your own. Yes. Yes, because it's. Still a lot of struggle with it. It's good.
So,
You've done it. Okay, so when you were getting the partial differential, you don't in because it gives you numbers and then the derivative numbers are zero. So when you create Jacobian, treat it as it has only variables. Then once you have the Jacobian matrix, you plug in values. This is wrong. That doesn't matter. So here you. No, don't. So don't put the values in there. You need to have a generalized. First, you have to have again, please, okay, can we just listen up? So for your class reservation, the example I showed you, or any other examples, when you want to have, like, you want to implement numerical values, first you have to solve it with the variables. Your numerical values are one example of some scenario, right? You solve this only with theta 1, theta 2, L1, L2, do all the differentiation. You will have a matrix 2 by 2, sorry, 2 by 2. Then you can put the values in, like what I did in the previous example. Otherwise, you will get some zeros that they shouldn't be zeros for your Jacobian. Jacobian is a mapping, all right? So don't replace anything until you have your Jacobian matrix. All right. All right, now this is, so you put them on here. Now this is your matrix with all the Well, now in your CV2, you have L1, L2, theta 1, and theta 2, which you will put in here. Then this becomes the matrix that maps the joint velocities and effective velocity, right? So your job is to put those numbers down in there. You need to submit class registration, Google Class, and okay, if you miss this one part, you can think about the other part. For the singularity, there are two presentation. Again, there's one always mathematics, right? The determinant has cases that that have. But what does it mean for more? So if you have a robot that at some configuration, the robot or your end effector loses rotation or motion station about an axis or motion along an axis, then that is this effect. Meaning what? So I'm going to tell you about one case and I want to think about the other case. If you put the determinant, you will see the other case. So think of it, theta 2 was 0, right? My end effector will only change effector once, so I'm taking off one theta, right? So it cannot reach this position. It has to make sure that theta 1 is in that. It's losing one in theta. That's one case. Now there's another configuration that same thing happens. I want you to think about it. One simple way is you found a matrix, right? With the variable of those, and then you get the determinant of that, put it equal to 0, all for theta 1, theta 2, and then you would know what configuration. Okay? So for the class participation, just think about what other scenarios could be. You only need the one to the people you can't submit that as your process. I want you to think about what is the other case that the robot loses like an ability to move. So that's the and food for thought. If we had like 3 by 2, the because the determinant, but there will be cases that if you can be related but you can't always rely on the mathematics. You have to actually understand. So things to do. You have a numerical value for your Jacobian and think about what's the other case that you're losing. The ability to move. And that is in here. Probably the difference started. Makes sense, right?
Yeah.